Let's solve logarithmic equations. So for example, let's solve log base 8 of n equals 4/3. So as our first step, we want to isolate the log expression. And in our case, it's already by itself, so we don't need to do anything else there. And then our second step, we will rewrite this in exponential form. When we do that, we get 8 to the 4/3 power equals n. And this is our solution, but I'm going to evaluate this, and I'm going to do it without a calculator. So remember, 8 is equal to 2 to the 3rd power, so I can rewrite this as 2 to the 3rd power to the 4/3 power equals n. Power to a power, I'll multiply my exponents. 3 times 4/3 is 4, so 2 to the 4th equals n, or n equals 16. Now with log equations, we do need to check our answer. So I will substitute 16 in for n into my original equation. Log base 8 of 16 equals 4/3. One thing that I'm really checking for is this argument greater than 0? Because the argument cannot be 0, it cannot be negative, it must be positive. Ours is, so when I put log base 8 of 16 into my calculator, I should get 4/3, and I do. So this checks out, and 16 is our solution. Let's look at a second example. 2 times the log base 4 of x minus 1 plus 7 equals 12. So we do need to isolate our log expression, and I will start that by subtracting 7 from both sides. And then I get 2 log base 4 of x minus 1 equals 5. And now we need to divide both sides by 2. And we get log base 4 of x minus 1 equals 5/2. Now that the log expression is isolated, I will rewrite this in exponential form as 4 to the 5/2 power equals x minus 1. We'll get x by itself by adding 1 to both sides, so x equals 4 to the 5/2 power plus 1. I can write 4 as 2 squared, so 2 squared to the 5/2 power plus 1, or 2 to the 5th plus 1. 2 to the 5th is 32. 32 plus 1 is 33, and that is potentially my solution, but remember, we need to check our solution. So going back to our original equation and substituting 33 in for x. So does 2 times log base 4 of 33 minus 1 plus 7, does that equal 12? So 2 times the log base 4 of 32 plus 7, does that equal 12? The log base 4 of 32 is 2.5. So 2 times 2.5 plus 7, does that equal 12? 2 times 2.5 is 5, so 5 plus 7, does that equal 12? Yes, it does. And 33 is our solution. Okay, let's look at a third example. The log of 3x plus 1 equals 2. So here we do have our log expression isolated. The base here on this log is 10, so rewriting this in exponential form, we get 10 squared equals 3x plus 1, or 100 equals 3x plus 1. Solving for x, subtracting 1, we get 3x equals 99. Dividing both sides by 3, x equals 33. Let's check our solution. So log of 3 times 33 plus 1, does this equal 2? The log of 99 plus 1, does this equal 2? The log of 100, does this equal 2? 2 equals 2, so yes, the solution checks out. And x equals 33 is our solution. Okay, let's look at a fourth example. The natural log of x plus 3 minus 1 equals 2. Let's get the log expression by itself. I will add 1 to both sides. We get the natural log of x plus 3 equals 3. And now we will write this in exponential form, Remember, the base on the natural log is e, so this becomes e cubed equals x plus 3. And getting x by itself, subtract 3 from both sides, x equals e cubed minus 3. This is my exact solution, or this is approximately equal to 17.1. We do need to check our solution, and I'm going to use my exact solution to check. Otherwise, we will have some round-off error. So the natural log of e cubed minus 3 plus 3 minus 1, does this equal 2? So the natural log of e cubed minus 1, does this equal 2? The natural log of e cubed is 3, so 3 minus 1, does this equal 2? 2 does equal 2, so yes, my solution checks out, and x is e cubed minus 3. Okay, so we just looked at 4 examples solving logs algebraically. Let's look at an example where we are solving it by graphing. So we've got the equation log base 2 of x minus 3 equals 2. Now, we saw this in the Explore journal. This is the graph you saw. And I created it to solve this equation. So I have y equals log base 2 of x minus 3 as my first equation. I have, remember we put y equal the left-hand side. And then I have y equals 2, or y equals the right-hand side as my second equation. And we are looking for where they intersect. Those two graphs intersect here. Again, you might need to zoom in or zoom out or change the scale to find the intersection point. Ours was easier to find. And if I click on the point of intersection, it tells me that my intersection is at 7, 2. So that means my x value is 7, and that's my solution. I don't need to check it because I have graphed the original equation, and so I know it does actually intersect there.